Okay, in this video we're going to talk about some basic probability concepts. You can think of the word probability as another way of saying what's the likelihood an event will happen. So if we were going to make a formula, we'd say the probability of some event A happening, that is the number of favorable outcomes, meaning the number of times that thing that you want actually could happen, divided by the total number of possible outcomes. So a common example we use would be the rolling a six-sided dice. So when you think about the different possibilities of rolling dice, it's either going to land on 1, 2, 3, 4, 5, or 6. This list of possible outcomes we call the sample space. So that's going to be the bottom of our fraction when we think of and when we're asked about different probabilities. So the probability of rolling a 4, for example, well, the number of favorable outcomes, that's just one of them. There's only one favorable outcome. That would be if we roll a 4, but there are 6 total outcomes. So the answer to number 1, the probability is 1 out of 6, 1/6. You can write these probabilities as fractions, or you can convert it to a equivalent decimal, or you can even convert that to an equivalent percentage. All of these mean the same thing. All right, the next question, well, what's the probability of rolling an even number? Well, let's think about that for a minute. How many even numbers are there? There's 2, 4, or 6. So again, the number of favorable outcomes, there's this one, and this one. There's 3 favorable outcomes out of a total of 6 possible outcomes. So if we were to simplify the probability of that, rolling an even number is 1/2, which we could write as 0.5, or we could write as 50%. Okay, the last one, the probability of rolling more than 3. So the probability we roll the dice 1 and it's more than 3. Now that means not equal to 3. I put the roll is more than 3. So that's similar to just saying you either rolled a 4 or a 5 or a 6. How many successful outcomes are there then? Favorable outcomes, a 4, a 5, or a 6. That's 3 favorable outcomes out of a total of 6. Again, coincidentally, that's also 1/2, which is 0.5 or 50%. Okay, so that's the basics of probability. Of course, we'll get a little bit more complicated on the next slides. Okay, this next problem is similar. We've got 2 apples, 5 oranges, and 6 bananas. So sometimes they don't tell you the total. We have to add them all up to realize that in total there are 13 pieces of fruit. Okay, so now we can read the question. What's the probability of picking an apple? So again, when they are asking the probability of an apple, that's the number of favorable outcomes, so there's 2 apples, out of the total number of outcomes, which is 13 pieces of fruit. Okay, the probability of picking a banana, how many bananas are there? There's 6, so 6 favorable outcomes out of a total of 13. Okay, this last one gets a little bit more complicated. It says, what's the probability of picking a fruit that's not an apple? Well, there's a few ways you can think about it. We can write it this way, probability that it's not an apple. That's actually called the complement. And when you have the probability that it's not an apple, you can just say, well, that's 1 minus the probability that it is an apple. In that case, that's 1 minus, we already calculated the probability of an apple, 2 out of 13. If you put that in your calculator, you would get the probability that you don't pick an apple is 11 out of 13 times. Now you can think about it another way, however. You could think to yourself, well, if it's not an apple, that would be the probability of picking a orange or banana. And we'll talk about this more in the coming slides, but you can always think of or when we're talking about probability as a plus sign. So the probability of orange or banana is going to be the probability of an orange, which is 5 out of 13. The probability of a banana, 6 out of 13. Look, we end up getting the same answer that we got doing it the first way. Either is fine. Okay, let's look at another example. This one is called empirical probability. And it's a little bit different than rolling a die or picking something out of a basket of items. It basically is taking historical data, so data we collected from the past, and using that data to make probability predictions. But again, it's still the same formula where you say the probability of any event is just the number of favorable outcomes divided by the total number of possible outcomes. And again, you can see in this table, one thing that is missing that we're going to need is we've got students and their grades, but we must add them all together because the total is what's going to be the bottom of any probability fraction. So let's add those. Okay, it's 1710. So now when they ask, what's the probability if we select a random student that they got a D grade? So we look at the favorable outcome is getting a D grade. How many of those favorable outcomes were there? There were 210 divided by 1710. And usually when the fraction is kind of with big ugly numbers, it's usually preferable to write it as a percentage. So we'll make it into a decimal and then multiply that by 100 to get the percentage. And we get approximately 12.3%. So if we picked a random student out of our historical data, the probability that that student got a D was 12.3%. Okay, now we have an OR question, which hopefully by now we have realized if you have an OR question, the probability of an A or a B is going to be the probability of A, or in probability usually translates to mean plus the probability of B. So probability of A is 200 out of 1710. The probability of B is 450 out of 1710. That's 650 out of 1710, but we'll need to, just to make it a little more readable, just convert that to a percentage. So we convert it to a decimal and then multiply by 100 and we'll get 38%. So if we picked a random student out of our historical data, 38% likely that we would pick a student who scored an A or a B. Okay, so here's some more examples. We did talk about the complement rule, but we'll do it again. The probability that something doesn't happen is exactly the same as 1 minus the probability that it does happen. So in this example, what's the probability of selecting a student who did not get a D? We want the probability of not getting a D is going to be exactly the same as the 1 minus the probability of getting a D. So we've got 1 minus 210 students got Ds out of the 1710 total. So we'll put that in our calculator, and it turns out 0.877, which is 87.7% is the likelihood that the student did not get a D. So similarly, if we want to know probability of a student that we picked randomly did not get an A or a B, so the probability of not an A or a B is going to be 1 minus the probability of A or B, which is 1 minus, remember the probability of A was 200 over 1710, or in probability usually translates as a plus, 450 over 1710, oops. And we'll put that in our calculator, and it ends up being about 62%. If you wanted, you could have also calculated as, instead of saying the probability of not getting an A or B, you could say the probability of C or D or F. If you went ahead and calculated that, you will get the same answer. 800 out of 1710, 210 out of 1710, and 50 out of 1710. When you calculate it, you end up getting the same answer. Okay, we'll do a lot of problems like this where you see a whole table of information. And I often like to kind of draw a box here because the box represents the people we actually surveyed. So each person you surveyed is standing in one of those boxes. For example, there were 40 men who prefer soccer. There were 30 women who preferred soccer. These numbers going down this way are the totals. So we could look and say, look, total in our survey, whether male or female, 70 people preferred soccer. Or we can say total in our survey over here, there were 100 men, 150 women, and so on. So when they say, well, what's the probability a student prefers soccer? They did not mention that they care at all whether they are male or female. So we will look at the total number of soccer players. So the probability that they preferred soccer is the number of favorable outcomes, which 70 of the students in the survey preferred soccer. This number here is the total number of students in the survey. And if we were going to convert that to a percentage, that would be 28% of the students in the survey prefer soccer. What's the probability that the student prefers art? Again, it doesn't mention male or female, so we will look at the total number of art students. The probability the student prefers art, the number of favorable outcomes. So there were 30 people in the survey who preferred art. We don't care if they're male or female. There were 250 total, and so we get 12% of the students in the survey prefer art. Lastly, they ask us, well, what's the probability the student is female? Again, in this case, we're not interested in soccer, basketball, science, art. We're only interested in whether the student was female or not. So the probability the student was female, there's a total of 150 females out of 250 possible students, and so that translates to 60%. All right, this is the same table, but now they're going to ask us some questions about joint probability. Joint probability just means they're giving you two characteristics at the same time. So the first question asks, what's the probability that the student is female and prefers art? So these are all the female students. These are all the students who prefer art. So there are 20 students who are both female and prefer art. So the probability of female and art, there are 20 out of the 250 students who have both of those traits at the same time, which is going to be 0.08, which is 8%. All right, it asks now, what's the probability the student prefers basketball and is male? So here's all the men, here's all the basketball players. To have both of those traits, there are 20 out of the total 250 of all the people in the survey. So coincidentally, that is also 8%. Okay, we've already talked about this a little bit, but I want to remind us all, when you see the word or in probability, usually you want to think about adding the individual probabilities. So we'll start with some simple examples. The probability the student prefers either soccer or basketball. So we would do the probability of soccer or plus the probability of basketball. So we look back up at the table, there's 70 out of 250 soccer players and 70 out of 250 are basketball players, which is 140 out of 250. If we wanted to turn that into a percentage, that is 56% are either soccer or basketball players. Okay, similarly, we could ask, well, what's the probability that they prefer either art or science? Okay, same thing. Probability of art plus the probability of science. We will look at these. Art is 30 out of 250. Science is 80 out of 250. That becomes 110 out of 250, which is 44%. One thing I want to mention, because on the next slide it will be a different situation. In each of these questions, these two choices are what we call mutually exclusive, which means you either prefer soccer or basketball. You do not prefer both at the same time. Similarly, you either prefer science or art, but it's not the case that you prefer science and art. So that's called being mutually exclusive. It can't be both. On the next slide, we're going to have some questions where it's possible that we're choosing between two things, but it's possible that you could be in both categories. So let's look at the first category. The probability the student is male or prefers science. So here are the males. Here are the people who prefer science. And you can see there is one place where we have students who fit both categories. So these two categories are not mutually exclusive. It is possible to be both male and prefer science at the same time. When that happens, the formula we use is just a little bit modified. So in the case where we're trying to find the probability of A or B, and they're not mutually exclusive, meaning it's possible to be both, like normal, we add up the probability of the first plus the probability of the second, but then we subtract the people who are in both categories because we've counted them twice. So let's do this example. Probability that they are male or prefers science. So the males are 100 out of 250. The probability that you prefer science, so this or, is 80 out of 250. The problem is, in this case, I counted these people twice. So I must subtract them so I don't double count, and then we will get the final probability, which is 150 out of 250, which is 60%. Okay, let's look at the next one. Probability that, I'm going to go ahead and erase this so we can look at the next one with a clean slate. The probability that the student is female or prefers art. Again, they're not mutually exclusive because it's possible to be both. So the probability of being female is 150 out of the total, which is 250. The probability of preferring art is 30 out of 250, but we must subtract the people we double counted, which is that 20 out of 250. So in the end, we will get 160 out of 250, which is 64%. Okay, let's look at the last one. Probability the student prefers soccer or basketball. I threw this on this slide so as not to trick you, because if you look at these, they don't have any overlap at all. So we could do this same formula still. We'd say the probability of soccer is 70 out of 250. The probability of basketball, also 70 out of 250. The probability that you do both soccer and basketball, if we're going to stick with this formula, in this case it's 0. There's no chance you can do them both at the same time. So this actually would have been a question more appropriate for the previous slide when they're mutually exclusive, but that's okay, we can still figure it out, and we get 56%. Okay, we're going to move to a new topic called independent events. And events means you're doing more than one thing. More than one thing is going to happen. And I'll give you a hint. It's called the multiplication rule. Usually when you see the word and, or when you think of more than one thing happening, this first thing and the second thing, you want to think about multiplying. So let's talk about the most simple examples are always rolling dice. So we're going to roll a die 2 times. So we're going to have something and something else. What's the probability of obtaining 2 6s? So it's the probability of a 6 and the probability of a 6 a second time. So these are what we call independent because whatever happens on the first roll does not affect what happens on the second roll. So the probability of rolling a 6 the first time is 1/6. The probability of rolling a 6 the second time is also 1/6. You multiply that straight across and we get the probability, if we roll the die twice, of rolling 2 6s is 1 out of 36. Okay, the part B is a little bit more complicated and let's see how. It says that what's the probability you roll a 5 and a 6? So let's think for a minute. There's actually 2 different ways to roll a 5 and a 6. You either roll a 5 and then a 6, or you roll a 6 first and then a 5. So we need to think about it. It's the probability of a 5 times the probability of a 6, or is plus the probability of 6 and the probability of 5. So let's stick those probabilities. This is just 1 out of 6 times 1 out of 6 plus, this is also 1 out of 6 times 1 out of 6. So it's 1 out of 36 plus another 1 out of 36 becomes 2 out of 36, which is 1 out of 18. Okay, the next example gets a little bit more complicated. It says we have 10 red markers and 5 blue markers in a bag. So I drew that. And what they're going to ask now, it's called dependent events. And what that means is if we're going to have 2 different things happen, it turns out that sometimes the second event is dependent upon what happens in the first event. And I'll show it to you by doing an example. So it looks like we're going to pull 2 markers out of the bag. And I will say this, it doesn't say these words, but this is implied, without replacement. And what that means is I take 1 marker out and then I keep it with me. I don't put it back. And then I take the second marker. So when they ask about the probability of 2 red markers, let me show you how to write it. Since it's 2 events, it's going to be the probability of red times, because that's the first thing. We'll pull out the red. What's the probability? But now the second probability is dependent on what happened in the first probability. So it's the probability that the second time we pull out a red, given that we pulled out a red the first time. Let me explain. So again, the number of favorable outcomes, the first is 10. There's 10 markers out of a total of, looks like 15. Now, the second time I pick a marker out, I've already taken 1 out. So there's only 14 markers left. And hopefully I've already taken a red marker out, which means there's only 9 left. So now we calculate that dependent probability, those 2 events happening, and it's about 43%. Okay, let's look at the next question, which of course even gets a little bit harder. The probability of red and blue. So again, remember there's 2 ways to do it. You could pull a red first, and then you could pull a blue, considering you already pulled a red, or, which is going to be plus, you could pull the blue first, and then you could pull the red second, considering you already pulled the blue first. So let's put these numbers in. In the beginning, the first one's easy. 10 out of 15 are red. But if we pulled a red out, there's only 14 left over, but there's still 5 blue markers, or becomes plus probability of a blue. So instead, if that didn't happen, instead if we pulled a blue first, that's 5 out of 15, times the probability of a red. So after we picked that first blue, there's only 14 left, and but there's still 10 reds we could choose from, which is about 48%. Okay, conditional probability. We just talked about it on the last slide, but we'll talk about it a little bit more. So you read this as saying the probability that B happens given that A has already happened. And it gives you a formula for that. Let's see how it plays out. Calculate the probability that the student is a female given that she plays basketball. So it's the probability she's a female, but we already know she plays basketball. So according to the formula, that is the probability that she is both female and plays basketball divided by the probability that she plays basketball. How many people are female and play basketball? That's 50 of them. And what's the probability of playing basketball? That's 70. Okay, which is 71.4%. Okay, let's look at the next one. Probability the student prefers soccer given that the student is male. So that's the probability of soccer and male divided by the probability of being male. So given that the person is male, let's just look at all the males. There are 100 of them total, and the ones who are male and they like soccer, there are 40, so that's 40%. Okay, last one, similarly, given that she is a female, what's the probability she takes science? So that's the probability of both science and female divided by the probability of being female. So how many people like science and were female? That's 50. How many total females? That's 150. And so we get 1/3, which is about 33%. Okay, let's do a review. Let's see how many other ways they can ask us about these concepts. So first one, a coin is flipped, a dice is rolled. To me, that sounds like independent events. So we want the probability of a head on the coin and a probability of 4 on the dice. So the probability of head and the probability of 4. Remember, and is times. Probability of a head is 1 out of 2. Probability of 4 on the dice is there's 1 4 out of 6 choices. So that total probability of those two independent events is 1/12. Okay, looking at this next question, a bag contains 50 items, 15 are defective. So, and we're going to pick the probability of choosing 2 defective items in a row. Those seem dependent. When I say dependent, it means, okay, the first probability of picking a defective item, it's just 15 out of the 50 were defective. However, the second defective item, we have to take into account that we already picked a defective item out. So on our second pick, there's only 49 defective items left, and there's only 49 total items left, and only 14 defective items. So the overall probability of picking 2 defective items in a row is about 8.6%. Now it's asking the probability of finding a white car in the parking lot is 60%. Find the probability of picking 2 white cars. Now this is a really big population. It doesn't tell us how many white cars there are total. In that case, you treat it like an independent event, in which case it would be a probability of 36%. Okay, let's put all the ideas together. Here's another contingency table, and we've got lots of questions to go through. So let's start on the first one. If a person with a side effect, so any of these, stomach, cough, headache, is randomly selected from the study, what's the probability he had a headache? So again, we're not interested in whether he took drug 1, 2, or 3. So all the people who had a headache, there were 74 out of a total of 173, which is about 43%. I'm just going to round to the nearest whole number percent. Okay, let's look at the next question. What's the probability that a randomly selected person had a stomach ache or a cough? So remember, with or, we're going to be adding. So the probability of a stomach ache is 55 out of 173. And the probability of a cough is 44 out of 173. And when we do that calculation, that becomes approximately 57%. Remember, by the way, for this or, these were mutually exclusive. There's no one person who had both a stomach ache and a cough, so we don't need to worry about subtracting any duplicates. Okay, let me erase these. Moving on to number 3. What is the probability of selecting someone with a cough or someone who took drug number 3? Now, look here. These are not mutually exclusive. There is a group of people who have both of those traits. So again, the or, someone with a cough. So the probability of a cough was these 44 out of 173. Probability of taking drug 3 is 38 out of 173. But because these are not mutually exclusive, you must subtract the people that you counted twice. You double counted. So that's subtracting 13 out of 173. And that is approximately 40%. Okay, let's look at the next one. So I'll erase all this. Given that the person had a headache, so we're looking at a probability and we know he had a headache. What's the probability that the person took drug number 2? So that's the probability that they took drug number 2 and had a headache divided by the probability of a headache. So all the headache people. So the probability of drug 2 and a headache is 50. And the probability you had a headache, so all the headache people were 74, which ends up being about 68%. So if you knew the person had a headache, it was 68% likely that they had taken drug number 2. Okay, let's move on to the next question. What's the probability of picking a person with a headache followed by a person with a stomach ache? Now that means we're doing 2 choices, but these choices are not independent, they're actually dependent. Why? Because after you pick one person out of the group of 173, the next choice you make, you're choosing from a smaller number of people because you already took the one person out. So the probability of a person with a headache followed by a person with a stomach ache. Well, firstly, the headache people, that's 74 out of 173. Followed by, so this we multiply by the probability of the second event. But just remember, the second event, there's only 172 people now that we're choosing from. And the second event, they want stomach ache. Okay, so that's 55 people with the stomach ache. So when we calculate that, we get approximately 14%. Okay, let's look at the next question. It says, what is the probability that we're selecting one employee, so it's not 2 different events, just we're selecting one employee, he had a cough, and he took drug 2. So that just means he has two traits, he had a cough. So here are the cough people. And he took drug 2. So here are the drug 2 people. So there are 20 people who have both of those traits. So it's going to be 20 out of the total number of people, 173, which if we're rounding to the nearest whole number percentage, that's a little bit less than 12%. So we'll say 12%. All right. And lastly, it says, what's the probability of selecting an employee who had a stomach ache and took drug 1? So again, let's clean all this up. Stomach ache and drug 1. So we're just picking one employee. We're not doing dependent events. So if he had a stomach ache and he took drug 1, that's these 10 people. 10 out of a total of 173, which is a little bit less than 6%, but we're going to round it to 6%. I think it's about 5.78, but we'll say 6%. Okay, hopefully all of these different practice problems help you understand probability.